Actually, come on. No, they're not.
All the lights are on.
Okay.
Take the sunglasses off.
Right. So, sorry, Penka, I will not repeat what I said yesterday. I will just continue where I ended up yesterday. And remember, for the existence result for Stein structures, there was two steps. First, one needs to extend an integrable complex structure over the handle, and then one needs to extend a J-convex function over the handle. And I started explaining the second step. So I will continue that and then move to the first one. So suppose that, what we already convinced ourselves of yesterday was that it all comes down to constructing just a one J-convex hypersurface on a standard handle where this is real Rk and this is R to n minus k in Cn with a standard complex structure. We want to construct one I-convex hypersurface which is going over the handle like this. So, and it should be co-oriented this way. So this is the goal, sigma I convex. Okay. And once we have that, then by the max construction, we can construct a J-convex function on the handle which extends a given function down here. So the hypersurface sigma should match level sets of some standard function down here, so we can implant it in our manifold and then bend around like this. Okay. So let me first introduce just some coordinates to describe this situation. So let's say coordinates here are z, j is xj plus I, yj. Those are complex coordinates on Cn. And let me introduce the norm in the Rk direction as capital R. Where that? So actually, I think I'm used to drawing pictures such that this is the imaginary direction. So this is y1 square all the way up to yk square. And little r is all the other coordinates. So it's x1 square plus xn square plus y k plus 1 square plus yn square. And then if we look at the function phi standard, which will just depend on these two parameters, which is a little r square minus capital R square for some constant a, then it's easy to see that if a is bigger than 1, this function is going to be I-convex. Yeah. So you see this function, this is a quadratic function, and it is decreasing in k direction, and it's increasing in the other directions. And if to check I-convexity, you look at every complex pair, say x1 and y1, and now it's decreasing in the y1 direction. It's increasing in the x1 direction, but it's increasing faster in the x1 direction, and the average is hence positive. And this This is precisely eye convexity. Yeah? So of course, I mean, this you can just compute and take it as, yeah. If you don't like the geometric picture.
There would be a problem if there were more than half a dimension.
Yeah, then you couldn't do that, right? Yeah, then you couldn't do that. So this is a level set. So let's say down here, this is a level set where this standard function is equal to, I guess, equal to -1. That's the level set that would continue through here, if this is -1. Yeah. So this is one level set of the standard function. We want sigma to match that level set and then bend around. And we will find this hypersurface also as being described just in terms of these two coordinates, which is nice because it brings down to just two variables. So we will describe sigma. In fact, we will write sigma basically as a graph where capital R is some function phi of little r. Now this phi is not a J-convex function here, so maybe I shouldn't use the same. But now this is just some function describing a hypersurface in Cn. Yes. Yes, it's this level set, which is continuing like this here. Yeah, it's a level set of a quadratic function, but then we need to deviate here and bend it around.
But also same thing on the top.
Yeah, same thing on the top. This is also part of it. Yes. Mm-hmm. Okay. So if I draw this just in, now I can draw pictures just in these coordinates, R and capital R. And I want to construct a hypersurface which up here, now you need to, you need to look at this upper quadrant just. Yeah? So we want a hypersurface which looks like the standard quadratic function. Let me maybe draw it here. So it should match this one, and then it should deviate and it should bend down. And when I'm saying it's a graph, it will actually become vertical. Yeah, so never mind, but it's still, yeah. So the slope becomes infinity here. So this is what this hypersurface should look like. Yeah. Okay. So now one needs to make some rather lengthy computation and compute. If you describe a hypersurface like this, then you compute what is the condition for this hypersurface to be I-convex. Yeah. So sigma is I-convex. Well, you can compute exactly what it is, but it's getting surprisingly complicated. So it's in fact determined by two second-order differential inequalities. So I'm not going to write those down, but I'm going to write down some sufficient condition for I-convexity, which is simpler, which you can extract from that. So it's sufficient for I-convexity that the following, and this I cannot. At some moment I knew it by heart because we were using it so often, but now not any longer. So it's this inequality, phi double prime plus phi prime cube over r minus 1 over phi 1 plus phi prime square should be greater or equal to 0. Okay. So this is nice, right? So it's some differential inequality for a function of one variable, and you just need to solve it. And surprisingly, this is not entirely easy. Yeah? Well, okay, it doesn't look so bad, but okay. So there was one great simplification brought into this picture by Michael Struve at ETH when Cieliebak lectured on this. He had some very complicated construction of such things, and then Struve listened to that, and a day later Struve came back and wrote down a differential equation which had this marvelous property that first you can solve it, and second, the solution automatically satisfies this differential inequality. Okay? So it's okay. I was absolutely amazed. So this is Struve. No, I think there's just some incredible smartness behind that, and no, I don't think so. I think there are people who just stare at this differential inequality and realize you make it some differential equation, and yes. Okay, so I'm going to write down this differential equation. So it's Struve's differential equation is phi double prime plus you want to
soup and soup solutions work for this. So for this.
Yes.
I think that must be the trick.
Mm-hmm. Maybe.
Let's do that.
So this is it. So you just forget about this term, and you throw in a factor of 2 here, and look at this differential equation. Okay. So now you see this is just a first order differential equation in the derivative. So you can actually integrate it. Yeah. So let me just do it. So this is equivalent if I integrate it once to saying that 1 over phi prime square is equal to logarithm of r over delta, where delta is some integration constant. Yeah, so I just integrated and get a solution for phi prime, and then you need to integrate once more. So you solve for phi prime and integrate this to get a solution of phi. And then you just need to study what the solution looks like. But already what you see from this form here is that it is already starting out correctly, because at delta the derivative becomes infinity, and then for r bigger than delta it's finite. Yeah, so already this is a solution. It starts at some. We still have a choice of constant where it starts, and then it starts with slope infinity, and it's bending around. Yeah, so this is already having roughly the correct shape. So this is at delta we have slope infinity. So let me just do this. And now it turns out you can do the following. You can pick any linear function here. So r is, let's say you pick this equal to 1 plus d times little r. D is some constant greater than 0, but otherwise it can be arbitrarily small. And then you can adjust the remaining free constant in such a way that you have a solution which starts out at a value above this linear function, and then its approach. Well, sorry, I should be a bit more careful. So it starts out at slope infinity. It's always moving upwards, but then eventually it hits this one at some place. Okay. So this is hitting somewhere. And it turns out you can make the whole thing very small, because we need to make the whole handle also arbitrarily thin if we want to implant it somewhere. So maybe here's some parameter gamma which we need to, and say this is 1. This is some fixed size, and this we want to also be able to make small. So we can use that model. Yeah. So you can do it so that this is so small it's below gamma. Yeah?
Sorry, where did the delta come from?
The delta just comes. This is just the first integration constant.
Sorry.
Yes.
Okay.
So this delta is still at our disposal. Yes? Mm-hmm.
And when you hit that you adjust with delta, so you say choose, you know the gamma, you write,
you know the gamma, and say the gamma is somewhere here. And then there's actually a second constant coming in. So one is delta, and there's a second integration constant, which you can choose. And this determines how far out you are. So one way to describe it is that this is going up to some k times delta, and k is the second constant you get from integration. And then you're going to make delta very small, in fact, and you need to make k rather large, but by making delta very small, you can make k delta still smaller than any given gamma. So it's some playing around with constants. And if you choose delta and k appropriately, then the solution of this differential equation satisfies the differential inequality. So it defines an iconvex hypersurface. Okay? And it has roughly the correct shape. Now, the only thing missing, this does not yet match the quadratic function outside. Yeah? So what do we do about that? Let me redraw the picture here. So we have already a function. So we have a linear function going up like this. Then we have our solution, which connects with this linear function. And now we have the quadratic function to which we want to match it. So the quadratic function is doing something like this. Yeah? Okay? So unfortunately, you could try and just continue this solution until it hits the quadratic function, but this doesn't work. So you cannot go as far as you would need to connect to the quadratic function. So that's the first idea which fails. The second idea is, well, maybe you just connect it here to the linear function, then follow the linear function from here to here until it hits the quadratic function, and then follow the quadratic function. And here's where Helmut's whatever subsolutions come in. So if you have one solution and another solution, you can take the maximum of the two graphs, and that's still going to be iconvex. This is a version of the maximum construction I explained last time for iconvex functions. You can also take these functions whose graphs we have, and you can just take a maximum of this. This is iconvex. Yeah. So in principle, if this bit is iconvex here, if this bit is iconvex there, and that is iconvex anyway, because the standard function, you can just go like that. Yeah. Okay, that's the second attempt, which is already better, but still doesn't work, because it turns out this is iconvex up to here, up to the place it hits. The linear function is iconvex here. The quadratic function is iconvex, but somewhere in here, the linear function fails to be iconvex. This is only iconvex up to a certain point. Okay, and that point we were getting a little bit worried. Yeah, now it turns out you can follow. If you introduce one more different kind of function, then you can actually do it. Yeah, so you introduce a fourth type of function. So you follow the linear function a little bit, and then you take another function which I'm not going to write down, which then goes from here to here and is iconvex, and you can use it to connect. And then you just piece these things together. Yeah. So this is actually where a lot of detailed work is, and I'm still wondering whether there is not maybe just a much easier way of things, because it's rather lengthy. The whole construction takes up some 20 pages, really, if you put everything together. Yeah. But in the end, you find this function, so it's going from here to here to here to here, and you smoothen the corners, and then you have your desired iconvex hypersurface. Okay? This is roughly how the construction works. Any questions on that?
So you think it's so complicated because it's just a sufficient condition, right?
No, it's so complicated because the sufficient condition appears not to be enough to construct these interpolations. So for the yellow one, the sufficient condition is good. So it satisfies the sufficient condition, and that is fairly easy, the sufficient condition. Now it turns out for these other shapes in between, they do not satisfy the sufficient condition. So you need to get to the much more complicated sufficient and necessary condition. But this is two differential inequalities, and both of them much more complicated. And you actually have to work with those. Yeah. So right. So we didn't see how to do everything just with the sufficient condition. That's what makes it complicated. Yeah.
Convexity survives smoothing the corner.
Yes. Yes. It's again a version of the statement for J-convex functions. You have a continuous J-convex function. You can smooth it to make it J-convex, and you can just apply this here, and it comes down to you can smooth the corners here. Right. Yeah. Okay, so I think this is probably what I want to say about this construction of I-convex functions. So this would then, if you put everything together, take care of step 2. So once we extended complex structure over the handle, then we can also extend our J-convex function over a handle. Okay. Yes. Yeah.
So you had this solution of Struve's equation,
Yes.
then linear, and then a third function.
Yes. Shall I write it?
Can you tell us anything about that one?
I can. It's a function Q of R it's actually just some quadratic polynomial. So it's some constant b plus c r square for some appropriate parameters b and c. So this is not this is not the standard function. Remember, this here was a level set of the equation minus r square plus a little r square is equal to -1, which means that this function is given by r is square root of 1 plus a r square. Yeah, so it's this is not a quadratic function. It's a quadratic function with a square root, and here you take an honest quadratic function. I think actually we'd probably take this to be 1 also, but then some coefficients. And again, this is a function which is I-convex somewhere, but not everywhere. And you need to carefully estimate that it is I-convex in that part where you want to follow that function.
You also have to adjust the value of a.
No, in fact, you can start out fixing a value of a. Yeah. So, well, honestly, in the proof, we actually choose a fairly large. But then after the fact, we can show that then you can interpolate back to any given a. So the construction in the end works for arbitrary a, as long as it's bigger than 1. Yeah? Mm-hmm.
So the n equations, dimension 4 problems, they do not show up in this step.
No, they don't show up in this step. This step works in any dimension, also in dimension 4. Yeah?
So why does a linear function stop being I-convex? It's not linear, right?
It's not linear. It's I mean, because it's, I mean, the way this function describes the hypersurface is in terms of these strange coordinates. So it's not true even if a function is geometrically convex here when you draw it that it describes an I-convex hypersurface. This is not true anymore. Yeah. So you cannot really see it geometrically, but just by looking at the function. Yeah. I told you if you have a function on Cn which is geometrically convex, is also I-convex. That is true. But this is not it. So it's describing some hypersurface in terms of some strange coordinates. And then you cannot really see it. So being convex is not enough to describe an I-convex hypersurface. Yeah. Right. Okay. Then let me move to step 2. Second step is step 1, yes. Okay. So we want to extend a complex structure over a K handle. Where K is less or equal to N. Okay. So let me first describe the setup. So we have some suppose down here we already constructed everything, and I'm doing the inductional step to extend the complex structure over the next handle. So remember, we start out with some manifold with an almost complex structure. Now I'm ignoring what we constructed below. I'm viewing it as a cobordism, just saying that near the negative boundary we already have everything, and we want to extend it. So now we have this cobordism, and J is an almost complex structure on that cobordism. And near the negative boundary, let me just 1 second. So near the negative boundary, in the neighborhood of this, we have J integral already. Okay? Was that a question now? Okay. Yeah. And also, let me call this del minus of W the negative boundary. Del minus of W is also J convex, because we constructed this. This was a level set of a J convex function, which we already had. Now in this cobordism, we have a stable manifold of the next critical point. So we have some critical point here, and we have some disk, some k-dimensional disk, which is for me, I'm thinking of the positive gradient flow. So it's a stable manifold flowing into the critical point, into the index k critical point, yeah, of a Morse function. So this is we can parameterize this by a map from the k-dimensional standard disk. And again, I'm viewing this as the unit disk sitting in Rk, sitting in Cn. Okay. It's a real disk sitting in Cn. And now I want to explain, first of all, some homotopical obstruction. So what we have here is then F is a map from the k-dimensional disk and its boundary to W, and it's mapping the boundary into the negative boundary of W. Right? Yes. No, we have J everywhere as an almost complex structure, and it's integrable at the bottom. So what I want to do, yes, by inductive assumption, yes, it's already integrable here. So what I want to do, and it's important that we have an almost complex structure to start with.
W is down below this, and what you drew is the handle.
It's the handle, yes, but I just chose to call it W now because it's, yeah. Mm-hmm. W is the cobordism. This is W is the cobordism, and I just ignore the part below which I constructed before. I just call this cobordism W. That's okay. Yeah. So what I want to do is I want to deform this almost complex structure through almost complex structures to make it integrable in a neighborhood of this disk. This is the goal. Okay. Yeah. Okay. So and I want to apply some H principles. So let me maybe write the data that you need to check for an H principle. No, the disk is not totally real. And so what I want to do is, in fact, I want to make this disk totally real. And then afterwards, once the disk is totally real, then we will see that we can make J integrable. So the main step is in fact making this disk totally real, but it's nothing. It's not totally real at all. Yeah. So we want to make it totally real. So first, yeah. No, k is less or equal to n.
So if you talk about unstable manifold, you have to choose a metric here, right? So
Yeah,
far,
just any, doesn't matter. Yeah. Okay, so if we take the differential of f, then this at every point the differential defines a linear map, an injective linear map from the tangent space of the disk into the tangent space of W. Now let me, for the sake of argument, assume I trivialized all the bundles. So I can just write linear maps from Rn to Cn, and I can view linear maps by elements of a Stiefel manifold. So a linear map from Rk into Cn is just a k-frame in Cn. Because if I take the standard basis vectors of Rk and their images, those determine the linear map. And this is a k-frame in Cn. Okay? So assuming all bundles are trivialized, which you can do by making it standard somewhere, and then yeah, okay, let me not get into that. So then this is a map at every point of the disk. The differential gives me a k-frame in Cn. So this is the Stiefel manifold, which I will write as V2n, k. This is k-frames in R2n. Yeah, just real k-frames in R2n. Yeah, just k-frames in R2n. And on the boundary, this is not mapping into R2n, but it's mapping into R2n minus 1, into the tangent space of the boundary, which I also trivialize in the relative part. Yeah, so it's mapping the boundary into the tangent space. So it's a k minus 1 frame in V2n minus 1. Yes. So what we get here is an element in pi 2 of V to nk and V to n minus 1k minus 1. Sorry, pi k. Yeah? Pi k. And now there's also a Stiefel manifold of complex frames in Cn. Yes? Or which is the same as saying in R2n this is totally real k-frames, because a totally real k-frame is the same as a complex basis. Yeah? So there's a map from the Stiefel manifold Vnk complex. So this is complex k-frames in Cn. Yeah? Or as I said, the same as totally real k-frames in R2n. And then I can, on the boundary, I can take complex k-frames in Cn minus 1, k minus 1 frames. And there's natural inclusion maps of pairs, and they induce a map between homotopy groups. Yes. So on the boundary, what this would mean is I'm also trivializing the contact distribution in the boundary. So the boundary is J convex. As I explained yesterday, but failed to say, a J convex hypersurface, I said there's this distribution xi on it. The hyperplane distribution. And J convex precisely means this is a contact distribution. So and now I'm taking linear maps which map the boundary of the disk, so k minus 1 vectors, into xi. So Xi is a complex n-1 dimensional space. This is Cn-1. Okay? This is how to think about it. Yeah? So this is what you would get by taking the differential of an isotropic embedding tangent to the context structure. Yes? But so far, this is nothing about honest isotropic embeddings. This is just bundle theory here. Yeah? Okay? But this is where it comes from. So we have this map, and now just a computation of homotopy groups shows that this map is in fact surjective. So, no, okay, you just compute homotopy groups of Stiefel manifolds. Yeah, so you have this map is surjective, and hence you can lift this map to here. So, in other words, this map here is homotopic to a map which is in here. So df defines an element in here, and you can homotope it to an element which is in here by a homotopy which I will call capital Ft. Yeah. So these are just bundle maps. They're not honest embeddings or anything. It's just bundle maps. Okay. Now this is yes. No. No, I'll come to that. Be patient. No, this is still true for any n. Yeah. K less or equal to n. This is crucial, but this is true for any n. So this situation is precisely the homotopical condition to apply an H principle for totally real immersion or totally real embeddings. So you have an embedding which is not totally real. And its differential is not totally real, but the differential can be homotoped to a bundle map which is totally real. Yes? And is also doing the right thing in the boundary. And then there's an H principle which tells you that the original embedding can be isotoped through embeddings to a totally real embedding. Okay? This is a version of the H principle for totally real embeddings, which says that f, let's say this is f0 is isotopic through embeddings to f1, and f1 maps dk into w del mine w, and this is totally real. Okay, and all these embeddings, they are always transverse to the boundary. So maybe I should draw it here. So this is f0, and then you homotope, and f1 is something which is totally real and still transverse to the boundary. It's not becoming tangent to the boundary. So it's yeah. Okay.
So this homotopy can go far away from F0?
C0 close. Yeah. But the tangent direction has to change a lot. Yeah. But you can always keep it C0 close. Mm-hmm. So now once we have this, now we can extend the complex structure. So we take F1. This is a totally real embedding.
Is that H principle in Gromov's book?
No. But it can be deduced from Gromov's H principle. But it's not stated in this way, so it takes another page of argument to deduce it. But you don't really have to prove a new H principle. It formally follows from Gromov. But it's not exactly stated like this, because this is some relative version with this boundary, and this is not stated. But it formally follows from it. Okay. So now, first of all, if I look at the boundary, then the boundary is mapping into this hypersurface. And as I said, near this hypersurface, J is integrable. So I have a real analytic structure on the target manifold, and I can talk about maps being real analytic. So now I'm perturbing the map F1, which I have here, to make it near the boundary, make it real analytic. So F1 to make it real analytic. Near the boundary. Yeah? And you can always approximate a smooth map arbitrarily close, C infinity close by a real analytic one. So then, now once you have a real analytic map, you can complexify it to a holomorphic map of a small neighborhood. And so then you extend it to a map which I maybe call F1 tilde, which goes from a little neighborhood of the k-dimensional disk in Cn. So it's the disk times the 2n minus k-dimensional disk of some sufficiently small radius epsilon. So this is the neighborhood of the k disk into W, which near the boundary of this k-dimensional disk is holomorphic. Yeah? So now this is defined on an open subset of Cn, and you can make this holomorphic. Yeah? You know that any real analytic map you can complexify to a holomorphic map. Essentially, you just write down power series and use them as complex power series. Yeah? So this is nothing very deep that you can do that. Okay, and so now we push forward. Now here we have a complex structure. This is a subset of Cn. So we have the complex structure I, the standard integrable complex structure on Cn. Now you push forward this complex structure under the map, yeah, under this diffeomorphism. So it's still an embedding, yeah. You push it forward under this embedding. So on the image, you get some new integrable complex structure. So we precisely get on the image of this new one. This was F1, yeah. We thicken it slightly, then push forward. So on a neighborhood of the image, now we get an integrable complex structure, which matches the given one down here, because here the map was holomorphic. Yes? Okay. So we have precisely extended the integral complex structure from here to one on a neighborhood of this totally real disk. And now you want to still extend this integral one outside this neighborhood to match it with the given one outside some slightly larger neighborhood. And this you can do because now you have two complex structures, the original one, J, and the new integrable one, near a disk, and this disk is totally real for both of them. And then you can essentially linearly interpolate between these two. So here it's becoming important that it's totally real. Yeah. So then you can interpolate to the almost complex structure, just as almost complex structure. So this is just bundle theory. Just interpolate to the given almost complex structure outside some larger neighborhood, and also what you obtain, you can check is homotopic to the original almost complex structure. Then, yeah. So this is the construction, and so far still fine for n equals 2. Yeah.
So here you don't need k to be equal to n.
So yes. Okay. Very good question. Yeah. So I was slightly cheating here. So what we actually do is we first extend everything from Rk to a little neighborhood of Rk in Rn. So to make it n-dimensional. Yeah? So everything I said is completely correct if k is equal to n. And if it's less, then we first extend it to a little neighborhood of Rk in Rn. And then we complexify, and then we do all the rest. Yeah? So then, but you are right. If you don't do it in this way, then you run into trouble here. Because then you still have some complex normal bundle, and on that normal bundle, things might look different. And so you really make it half-dimensional first. And then everything is determined. You see, if you have a totally real submanifold, then J is completely determined because everything is turned out, and then you can interpolate between any two. Yeah, exactly.
And another question. So when you said that this map on k homotropic groups is
Yeah.
surjective, you use the fact that k is at most equal to n.
Yes.
It wouldn't be true for.
It wouldn't be true for larger k. Right. I think maybe for a little bit larger k. I think this is not quite borderline, I think.
It wouldn't make sense.
The entire construction doesn't make sense.
The left hand.
Well, anyway, sorry. No, yes. So the right-hand side makes some sense, but the left-hand side only makes sense if k is less or equal to n anyway. Yes, right. Mm-hmm. Okay, now. So it seems like we would be done with step 1. Yeah, with step 1, right? Okay, now it's integrable everywhere. Why? Because now you take a little neighborhood of this thing, and this is diffeomorphic to the whole thing. So you just apply a diffeomorphism to make this equal to the whole thing, and then it's integrable everywhere. Yeah.
So we're not actually interpolating to J.
So yeah, at this inductional step, it depends how you want to phrase it. Either you can say we keep this J just the same and we homotope it, but in fact you can homotope J to make it integrable everywhere. Yeah, by first make it integral in this neighborhood, and then you expand that neighborhood until it covers everything. There's still a homotopy of almost complex structures, and at the end it's integrable everywhere if you want. Yeah. No, it's not fixing the boundary. So if you want to further continue, yeah, but it's not fixing the boundary. But yes, how do you attach the next one, right? So what you then you homotope it to make it integrable everywhere here, and above, slightly above, you undo the homotopy and match it with the J which you already had on top of that. Yeah, and then you have a J which is integrable everywhere here. And it extends all the way upwards, so you can do the next step. No, but this is a good point. It's important that you always keep track of this homotopy class of J, because you need it. Otherwise, you might run into just homotopical obstructions of extending J over the next handle. It's important you already have it as an almost complex structure, so you want to keep that. Yeah. Okay. Okay. So this extends the complex structure. And now we extend the J-convex function, and we're done. And something is not right yet, because I promised you it will only work if n is bigger than 2. Yeah. So where does this come in now? So now we constructed a complex structure, which is a standard structure on the handle, and to apply our construction of J-convex functions, we need to be able to arrange that the boundary that we have, if you pull it back to this standard handle, then it looks like the level set of of this standard function that we had in step 2. Yeah? This is given by phi standard is equal to -1. This was the function. This was the standard function from which we can construct our J-convex hypersurface. So we have a level set of this standard function, and then we can somehow bend it around and construct a J-convex function. Yeah. Okay. So now, a priori, of course, there's no reason that it should look like this. So this is the last thing that one needs to arrange. Now let's just look at this situation. What does it mean? So if we have this, if it looks like this, then here we have the k-dimensional disk, the core disk of the handle. And if you look at the boundary of this core disk, then you see, well, if we have that, then for this we need that the boundary of this disk is a subset of this level set. And it must be tangent to the contact distribution. Because in this model, if you take a level set of this function, then you just compute that the boundary of this disk in the center is tangent to the contact distribution on this level set, defined by this function. Okay? So if you want to have any chance of matching it with this model, then, or maybe going back to this other notation, f or f1 of this boundary here must be isotropic. Isotropic meaning tangent to psi, tangent to the contact distribution. And it turns out, once you have arranged that the boundary is tangent to the contact distribution, then in fact you can modify it slightly further to really match this model. So this is some technical part which I will not explain. But the crucial point is first to make it isotropic. Yeah? No, it's not. Well, it was just no. This was just the part of the manifold that I constructed beforehand. It has some boundary. The boundary is J-convex. That's all I know. And I attached a handle extended complex structure over the handle. Now I can pull back everything to Cn, to the standard model in Cn. I pull back this hypersurface down there, and a priori I don't know anything. So when I pull it back, it will not look like this here. Yeah, it will look something else. But I claim I can then adjust it to equal this one, provided that to start with, this boundary was isotropic. Then I can do some further adjustment to ranges. So this is not very difficult. And yeah, exactly. Before you go pull it back to the handle, then there's no phi standard. Yeah, it's some abstract manifold. Right. Mm-hmm. So which means we need to improve this H principle, which I'm erasing. So that we can, and this is really the last ingredient of the proof. So the last ingredient is then to improve this H principle to make this disk totally real, but also the boundary isotropic. Yeah? So how does that work? So let's look at the boundary map. So I'm just switching back to the original F. So this is a map from the k-1 dimensional sphere into this level set. So this level set is 2n minus 1 dimensional. Yeah? And J-convex. So it has a contact structure. So this last step is pure contact topology. So maybe I call this sigma just some contact manifold like this. Okay, and what we have from the previous H principle, we have seen that we can formally homotope it. We had this with this homotopy of bundle maps of this one to bundle maps which become totally real. If we restrict this to the boundary, we get some homotopy. Let me call it G. Let's try to stick to my notation. Yes, G sub T to. So I mean dg. The differential can be homotoped to G1, which is isotropic. This is what the previous H principle says. It's totally real. It's mapping into the contact planes. Just the linear map. Yes. This comes back to the question you asked: why you had K frames in Cn-1. Cn-1 is the contact distribution, and I can push it to map into the contact distribution, the bundle map. Yeah. So G1, right, is isotropic mapping into the contact distribution. Now, this is again the formal setup for an H principle. So there is an H principle for isotropic immersions. There's an H principle for isotropic immersions, which says that G, let's say this is G naught, is homotopic through immersions to G1, which is an isotropic immersion. Now, if I can replace the word immersion by embedding, then we're done. This is what we need. We need to homotopy through embeddings. Why do we need to homotopy? Okay, so why do we need an isotopy of embeddings? Because we attach a handle along the images. So if we change the attaching sphere by an isotopy of embeddings, we always get the same manifold. But if you change it by immersions, then you attach and you get something different. You're just not getting the right manifold anymore. Yeah. So we really need an isotopy of embedding. So now, if K is less than N, we're in the subcritical case, then you can just perturb this a little bit and make everything embeddings. Just because the dimension, this is defined on something K minus 1 dimension, and this is so small, if you just generically perturb it, everything becomes an embedding. You need to be a bit careful to keep it isotropic, but you can. Yeah. So then it's fine. So the interesting case is K equals to N. Now, if K is equal to N, then you can still take the end point of this, G1, and that is still less than half dimensional, so you can perturb a little bit to make it an embedding. You can arrange that, an isotropic embedding, but the homotopy has precisely the dimension that you could have intersection points during that homotopy. So if there's an actual invariant, so there's an obstruction to making the homotopy GT an isotopy. Isotopy meaning through embeddings. And I'll finish today by stating this obstruction. This is the following. You define a map, let's call it capital gamma, from interval 0, 1 times S k minus 1 to 0, 1 times sigma, which is 2n minus 1 dimensional, mapping each t and x to t, and you take gt of x. So you make this homotopy GT into one map with one more parameter into a space. Now you see this is a, okay, now k is equal to n already. Yes? So this is n-dimensional, this is n-dimensional. This is now an immersion of an n-manifold in a 2n-dimensional space, which near the boundary, 0 or 1, has no self-intersections, because near the boundary you have embeddings. So you can count self-intersections in the interior, and you get some count with signs. So there's some invariant I, gamma, called the self-intersection index. So it's the sum over all intersection points with signs. And this is an invariant which lives in either Z or in Z2. Why? If this dimension, which is n, is even, then this lives in Z. Because you have intersection, you choose some orientation of this manifold here. You have two branches, you orient both of them, and you count, you check the sign. Now you do not have a particular ordering of the two branches if you have a self-intersection. You don't know which one is first, which one is second. But if the dimension is even, you switch the order, nothing changes. So you get a well-defined plus-minus sign, and you get a well-defined integer. If the dimension is odd, then picking one order or the other would change the sign, so you only get something well-defined mod 2. Okay? And now there's a theorem of Whitney, and I promised I'll come to the point where n must be bigger than 2. So which says that GT can be deformed to GT tilde, an isotopy of embeddings fixed at the endpoints, to an isotopy of embeddings, if and only if this number is equal to 0. And this if and only if is true for n bigger than 2.
And hopefully wrong for n.
It is wrong for n equals to 2. Because the proof of this is based on the Whitney trick, finding a Whitney disk, and for that you need high dimension. Okay? And using this fact, you can then kill the obstruction. And I will come back to that actually tomorrow, because I want to discuss this in some other context. And then you can also, for k equals n, make it an isotopy, and this way you finish the proof. Okay, I need to stop here. Thank you.